This is Jack Jackson. We're back again doing some more work with formally looking at limits. So before we go any further, let's back up and look at some things that we did in the last video, and we'll start with our formal definition of a limit. So it says that for real numbers c and l and a real valued function f, we say that a limit is x goes to c of f of x equals l if and only if for every real number epsilon greater than 0 there exists a real number delta such that if c minus delta is less than x, which is in turn less than c plus delta, but x is not c, then l minus epsilon is less than f of x, which is less than l plus epsilon. Here are a couple other ways of saying that this condition right here, c minus delta is less than x, which is less than c plus delta, but x is not c. Another way to say that is right here. 0 is less than absolute value of x minus c, which is less than delta. Another way to say it is x is in the interval from c minus delta to c plus delta, but x is not c. And just saying it in words, we could say x is within delta of c, but it's not c itself. Another way to say this condition here is to say it with absolute value like this. Absolute value of f of x minus l is less than epsilon, or in interval notation that f of x is in the interval l minus epsilon to l plus epsilon, or in words f of x is within epsilon of l. And so this last video we looked at this example where we had a linear function, and this one we're going to look at one where the function is actually undefined at the place that we're taking the limit. So we have 2x squared minus 9x plus 10 over x minus 2. We take the limit as x approaches 2, and I claim that that limit is negative 1. Now first of all, notice that when you plug in x equals 2, you get x minus 2 is 0, so this is dividing by 0. Clearly this function is undefined at x equals 2. But it turns out the limit exists. Since the limit does exist, that says that the point 2, negative 1 is a hole in the graph. Now, here's the task for us at the moment. Suppose that someone claims that we lied to them about this limit, that the limit is false, and that our choice of 1 for the limit is off by at least epsilon is 0.5. We want to fend off this challenge by selecting the largest possible value of delta so that the condition in the definition is satisfied. And then we want to illustrate this graphically and then formally show that the appropriate inequality in the definition is in fact satisfied. Now before we get going any further, we're going to look at this and see that f of x equals 2x squared minus 9x plus 10 over x minus 2 can be simplified a bit. We can factor the numerator with anti-FOIL factoring as 2x minus 5 times x minus 2. Multiply this out with the distributive property, or FOIL, and see that it does turn out to be the top here. Of course, we're going to think of the denominator as just being one fraction, or one factor, I should say. And so notice with the fundamental equivalence property of fractions, we can just cancel out the x minus 2's, and this becomes 2x minus 5, provided x is not 2. So the original function is equal to 2x minus 5 for all x's that are not equal to 2, and it's undefined when x equals 2. Now, the undefined x equals 2 is no problem for us because one of the conditions in the definition of the limit is that we do not let x equal 2. So really, at all the x's we're going to be concerned about, this function can just be replaced with 2x minus 5, which really means this is very similar to the last example, which is just linear. So we start by finding upper and lower limits for the y values that correspond to this epsilon in this limit, and they are l minus epsilon and l plus epsilon. L minus epsilon then is negative 1 for L, and epsilon is 0.5, so it's negative 1 minus 0.5 is negative 1.5. L plus epsilon then is negative 1, and then plus 0.5, which is negative 0.5. So if we graph y equals negative 1.5, we get a horizontal line, and the part of the graph that we're interested in should be above that line. And then we also graph y equals negative 0.5 as a horizontal line. That should be an upper bound, and so the y's we're looking for should be below that on the graph, at least the part that we're looking for. Now the original function is increasing, so its highest it gets is going to be on the right side of the interval, the upper right corner of the little box as we had before, and the lowest it gets is on the left side, the lower left corner. The upper right corner, since it's the right side of our interval, will be x is 2 plus delta, and the lower left is x equals 2 minus delta. So what we want to do is solve some equations here. We want to find where the graph crosses that upper boundary, L plus epsilon equals 0.5, that horizontal line, that's going to be where that crosses this 2x minus 5 crosses that. And of course, for all the x's that are not equal to 2, the y value of the original function is the same as just the y value on 2x minus 5. So we're solving this equation right here. 2x minus 5 equals negative 0.5. Solving that's pretty easy, right? Just add 5 to both sides. We get here 2x equals 4.5, and then divide by 2 on both sides. X equals 2.25. We can also find the same thing by graphing a horizontal line. Y2 is negative 0.5. Y1 is our original function. I just use the standard window here and do a calc intersect on the TI-84 calculator, and we find the same x value of 2.25. So we would stay within the required interval on the right side if we let this x value be 2 plus delta. So 2 plus delta equals 2.25, so delta equals 0.25, or 1/4. Similarly, we find a lower boundary to it by finding where the lower line, 2x minus 5, is the original function, equals L minus epsilon, or negative 1.5. And so we're solving that equation, 2x minus 5 equals negative 1.5. Okay, and so add 5 to both sides. That gets us to 2x equals 3.5. Divide both sides by 2. We get x equals 1.75. And again, you can also find that on the graphing calculator by letting y3 be negative 1.5 and calculating where that crosses this, the original graph. So we want to find these two corners here. And again, this is where is going to be the lower left. You can tell by looking at the graph here, for one thing. So it's going to be the lowest x value of our interval, which is 2 minus delta, is going to equal that x value of 1.75 that we got out of there by calculating the intersection or solving an equation. And so solving this for delta gives us delta is, again, 0.25 or 1/4. Now, if these two values of delta that we found up here and here were different, then we'd have to use the smaller of the two delta values. But since they're the same, we know what delta is. It's 1/4, or 0.25. So the largest allowable value of delta to defend against epsilon is 0.5, is the smaller of these two values, which is, again, 1/4. So we can illustrate this by graphing in the following way. We want to find our window settings. So our window setting goes from x min of c minus delta to x max of c plus delta, and a y min of L minus epsilon to y max of L plus epsilon. Well, let's work out what those are. Remember, c is 2 and delta is 0.25, so we get 1.75 and 2.25 for the two x values, which are what we had, which were these two x values that we just found earlier, right? And we'd already worked out what the two y values are. L minus epsilon is negative 1 minus 0.5, which is negative 1.5, and negative 1 plus 0.5 is negative 0.5, is L plus epsilon for y max. So you see that I've taken those four numbers right there and put them in this graph, the graphing window here, and graphed it. And what you should see, actually, you can't, there's a hole in the graph in the middle. You can kind of see the hole right here. Normally you can't really see the hole, but you can kind of see it there. As a little break, we would draw it as an open circle there if we do it by hand. And what we see is we're leaving the corners of our window right at the corners. If you've got the correct value, the largest allowable value of delta to defend against a given epsilon, it's the graph, and you set your window up like this the right way, what should happen is the graph goes out of the window at one of the corners, and then at the other one it either goes out the corner or on the side. But it does not leave the window at the top or bottom. Now, if I did this in the GeoGebra sketch that we used earlier, here is the new formula plugged in here, the C value of 2, the L value of negative 1, and we see where the hole in the graph is where all three of these things, the graph, what looks like the graph except for the hole, and these two vertical lines cross at the point 2, -1 is actually a hole in the graph right there. It's our limit point. This purple box going from L minus epsilon to L plus epsilon on the bottom of the top, and from C minus delta to C plus delta left to right, that purple box is exactly the same, exactly what we've graphed in this window up here on the TI-84. And again, we see it going out both opposite corners. So this visually confirms that we have chosen the right delta. Let's do it formally. So formally, what we want to do is show that if C minus delta is less than X, which is in turn less than C plus delta with X not equal to C, then we want to show that that makes L plus epsilon less than f of X less than L plus epsilon. Now let's put in the specific values of f of X, delta, and epsilon that we're dealing with. So C is 2, so that goes here and here. Okay. Delta is 0.25, that goes here and here. And of course, X is not 2, not C. And then here we have L of -1 here and here, and delta, epsilon of 0.5 here and here. And in here we have the formula for f of X. So we want to show when this first inequality here is satisfied and X is not 2, then we have to end up with that inequality being satisfied there. So a condition on the X's implies a condition on the Y's. So we start with this inequality here, and we hypothesize that that's true. Now we want to turn the middle into this f of X. Now remember, this f of X reduces to 2x minus 5, so we're going to start by turning it into 2x minus 5. To do that, we multiply all three parts by 2. Of course, multiply x by 2, you get 2x. Multiply the left side by 2, we distribute, and that gives us 4 minus 0.5. Take the right side, multiply by 2, and distribute. This gives us 2 plus 0.5. 2 plus 0.25 times 2 is 4 plus 0.5. There we go. And now we need to subtract 5 from the middle to get it to be 2x minus 5. But if we do that, we have to subtract 5 from each part here. When you subtract this 5 from this, we're doing 4 minus 5 is -1. Still have our -0.5. Here we do 4 minus 5 is -1 as well. So now we're at this point right here. We also note that x is not -2, so we can take the part in the middle and multiply the numerator and denominator by x minus 2. And as long as x is not 2, we can do that, and this is equal to 2x minus 5. But that, when we do FOIL in the top, or the distributive property, becomes 2x squared minus 9x plus 10, and so that is exactly f of x in the middle. And so that showed us what. So we were able to show that when this first inequality is satisfied, then this second one is satisfied, and that's how it's set up in the definition of the limit. So can we formally prove the limit? Well, to do it, we need to solve these equations not just for a specific value of epsilon that was given. Here we were given epsilon as 0.5. We were able to set up these equations right here and solve them. We need to solve these in general. So regardless of what epsilon is, we want to put f of x equal to L plus epsilon and solve to find that place where it crosses. And so this is 2x minus 5 equals -1 plus epsilon. Remember, L is -1, f of x is 2x minus 5, at least as long as x is not 2. So solving this for x, we add 5 to both sides of the equation and then divide by 2. Distributing the 2 over here, we get x equals 2 plus epsilon over 2. Now, we also know that this function is going up, so this says where the graph crosses that upper boundary is when x is 2 plus epsilon over 2, but it also needs to be at the corner, so that means the x also needs to be 2 plus delta. So we put 2 plus delta in place of x, and this gets this part right here, which we can solve. Okay. 2 plus delta equals 2 plus epsilon over 2. Subtract 2 from both sides, we get delta is epsilon over 2. So this kind of corresponds to the upper right-hand corner, no matter what epsilon is. Okay, over here, we can do the same thing for the lower left corner of our little box. We let f of x equal L minus epsilon. Again, L is -1, f of x is 2x minus 5. Same steps as before. add 5 and divide by 2, we get x equals 2 minus epsilon over 2. But this side, it's at the lower left corner, we know that x equals 2 minus delta. So 2 minus delta equals 2 minus epsilon over 2. Subtract 2 from both sides, we get negative delta equals negative epsilon over 2, so divide by negative 1. Again, we get delta equals epsilon over 2 in either case. So that's the delta we need. So what you have to do is you have to kind of do this work here before you start writing the proof. You have to find out what that formula for delta is in terms of epsilon. Once you have that in mind, then the proof basically writes out pretty straightforward like this. Given any epsilon greater than 0, let delta be epsilon over 2. Then if x is not equal to 2, then f of x equals 2x squared minus 9x plus 10 over x minus 2 can be factored and reduced to be 2x minus 5. So if x is not equal to 2, and 2x minus delta is less than x, which is less than 2 plus delta, then we want to turn this middle into 2x minus 5. To do that, we multiply both parts, all three parts, by 2, distributing on the left. So here's what we start with. Multiply well, first of all, just replace delta by epsilon over 2. Now start turning the middle into the function 2x minus 5 by multiplying by 2. So the middle becomes 2x. And over here we distribute the 2. 2 times 2 is 4. 2 times this cancels the 2 in the denominator. This leaves minus epsilon. And then similarly we get 4 plus epsilon here. Now subtract 5 from the middle. Means we have to subtract 5 from the other part. 4 minus 5 is negative 1. 4 minus 5 is negative 1. You'll notice these steps are just about the same as what we did when we had a specific value. Actually, they're really exactly the same that we did when we had a specific value of epsilon. Now we're just doing it in general. Now multiply top and bottom by x minus 2, which we can do if x is not 2, which we know it's not. That's hypothesized. And that's a property of fractions. And this is the same as the original f of x. And so we have, what do we have? We have, given any epsilon greater than 0, if we let delta be epsilon over 2, then if x is not 2 and it's within delta of 2, then we see down here that f of x is within epsilon of negative 1. So therefore, by the definition of the limit as x goes to 2 of 2x squared minus 9x plus 10 over x minus 2 is actually negative 1. And of course, we'd see that as the graph is a straight line with a hole in it at 2, 2, negative 1.